In a previous video, we reviewed a topic from general chemistry on thermodynamics. In this video, we're going to review the topic of kinetics. So, in that previous video, we talked about the fact that the sign of delta G, and particularly the fact that if delta G is negative, then that reaction is going to be product favored and is going to be spontaneous. So the reaction is going to occur in the forward direction. However, it doesn't tell us anything about the rate of the reaction, or it doesn't tell us about how fast the reaction is going to occur. Instead, the study of how fast reactions occur is called kinetics. And so some spontaneous processes can be fast, such as explosions, but other spontaneous processes can be quite slow. For example, the conversion of diamonds into graphite is actually a spontaneous process. So despite a popular ad campaign, diamonds are not forever. However, this process takes millions of years, even though it's a spontaneous reaction. So the study of what factors contribute to a reaction being faster or slower is the study of kinetics. So there are a lot of factors that can influence the kinetics or the rate of a reaction. In general, in order for a reaction to occur, molecules have to collide with one another, they have to collide with enough energy to react, and they have to collide in the proper orientations in order to react. And so a lot of factors goes into determining whether or how often these collisions happen and whether they'll lead to a reaction. And so we're going to look at each one of these categories. So in general, when we describe the rate of a reaction, it depends on the rate constant and then also the concentrations of the reactants. And we'll talk about what the orders are, these N and M, on the next slide. So the order of the reaction is represented by these exponents on the concentrations of the reactants. And some of the terminology we use, if there is only a 1 exponent, then overall that reaction is first order. Right? In this case, this reaction is first order with respect to A and first order with respect to B, but when I add the orders together, it gives me the overall order of the reaction. And so this reaction, 1 plus 1 is 2, so this is second order overall. Or this reaction would be third order overall. And so the orders of the reaction tells us how the reaction will speed up or slow down as I change the concentrations. If the reaction is first order with respect to A, then the rate of the reaction is directly proportional to the concentrations. And so if I double the concentration of A, then the rate is doubled. This reaction is second order overall, but it's still first order with respect to A. And so again, if I double the concentration of A, the rate is doubled. But now in this reaction, it's second order with respect to A. And so now if A is doubled, the rate is going to increase by 2 squared, and so the rate is going to be quadrupled. As another example, if we tripled the rate, 3 squared would be 9, and so the rate of the reaction would increase by a factor of 9. All right, so in general, if we increase the concentrations of the reactants, we'll speed the reaction up. Now, the rate constant, the K in our rate law, there are a lot of factors that influence that. In general, the bigger K is, the faster the reaction is going to be. I think in the last video, we looked at some of these reaction energy diagrams where we're plotting either the potential energy or the enthalpy or the free energy as the y-axis, and then the reaction progress or the reaction coordinate on the x-axis. Right? And this tells us how the energy changes as I go from the reactants to the products. And almost all reactions have this sort of increase in energy before we get from the reactants to the products. And this energy barrier is called the activation energy. The higher the activation energy is, the more energy the molecules need to have in order to react. And in general, the bigger the activation energy is, the slower the reaction is going to be, because it's going to be less likely that molecules, when they collide, are going to have enough energy in order to react. All right, and so I mentioned this on the last slide, but again, the lower the activation energy is, the faster the rate will be. The bigger the activation energy is, the faster the rate will be. Right? And I actually like these pictures because you can see, right, the relative energy of the reactants and the products doesn't really have any influence on the rate of the reaction. Right? It's the height of this barrier that separates the reactants from the products that determines how fast the reaction will be. Okay, so the activation energy is one factor that affects a rate constant. The rate constant is also dependent on temperature, and in general, raising the temperature will result in a faster reaction. Now, this is a different graph than we had on the last slide. This shows us the distribution of energies for molecules at a given temperature. And in general, when we're at lower temperatures, the average energy, which is represented by the peak in this distribution, is lower than the average energy at higher temperatures. And more importantly, if this represents the activation energy, right, we can see when we go to the red curve, when we go to the higher temperatures, more molecules tend to have enough energy to react. So the activation energy doesn't change with temperature, but when I increase the temperature, more molecules are more likely to have the required energy, and that will speed the reaction up. All right, another factor that influences the rate of the reaction are steric considerations. And we talked about steric hindrance. We talked about the conformational analysis of alkanes, and then also when we talked about cyclohexane and things about like whether the one of the two chairs would be more stable depending on the 1,3 diaxial interactions. And when molecules collide, right, we're making and breaking bonds. Well, if I'm trying to make a bond between a carbon and an oxygen, if the carbon and oxygen aren't near each other when the molecules collide, then we're not going to get a reaction. And so we'll talk about this more in later chapters, but it's just good to know that the shapes of the molecules and the orientation that they can collide will influence the rate of the reaction. All right, and the last thing I wanted to talk about quickly is catalysts. So a catalyst is a compound that we can add to our reaction mixture that speeds up the reaction without being consumed itself. That means we can use catalysts over and over and over again to speed up many instances of a chemical reaction. Enzymes are a specific example of catalysts. These enzymes are biological catalysts, and they're generally proteins. The way catalysts work, both enzymes and other catalysts, is they actually change the reaction mechanism. And so catalysts speed up reactions by changing to a new mechanism that has a lower activation energy. And we'll talk more about examining reaction energy diagrams in the next video, but the number of barriers that we have in the reaction energy diagram tells me how many steps a reaction is. And so, what this plot is representing is the energy diagram for some particular reaction without a catalyst that has a very high activation energy. And then when we add a catalyst, you can see the activation energy is much lower, and the mechanism changed. And the reason I can tell the mechanism changed is because the uncatalyzed reaction occurred in just one step because there's one hump, whereas the catalyzed reaction took 3 steps because I can see 3 different barriers. But all of the barriers are smaller than the original one, and it doesn't really matter how many barriers there are. All we're interested in what is the highest barrier. So this is the highest barrier, and so this will determine the rate of the reaction. All right, so in the next video, we've got more information about interpreting these reaction energy diagrams.